All right, let's talk about one of the biggest topics in all of chemistry, one that you absolutely have to know for your exams. I'm talking about redox reactions. Now, they might sound a little intimidating, but trust me, by the end of this, you're going to have a rock-solid grasp on what they are, how they work, and exactly how to crush any questions about them.
So, here's our game plan. We'll kick things off with why redox even matters. Then we'll get into the nitty-gritty, defining oxidation and reduction, learning how to track electrons with something called oxidation numbers, and spotting the 4 main types of redox reactions. After that, we'll cover the big one, how to balance those tricky equations. And finally, we'll connect it all to the real world and see how redox powers things like batteries. Sound good? Let's jump in.
Okay, first things first. Why are we even talking about this? Well, believe it or not, redox reactions are literally happening all around you and even inside you, right this second. They're kind of the hidden engine running the world.
I mean, just take a look at this. Burning gas in a car? That's redox. The battery that's powering whatever device you're using to watch this? You guessed it, redox. Even something as simple as metal rusting? Yep, that's a redox reaction too. It goes even bigger though. Think about how we get metals from the ground or make huge-scale industrial chemicals. All of it comes down to redox.
Okay, so we know they're everywhere, but what are they? Let's break down the 2 key players here, oxidation and reduction. We'll start with the old-school definition and then get to the modern one, which is way more useful. So, originally, chemists thought it was all about oxygen. If you added oxygen to something, that was oxidation. Simple enough. But that definition was a bit limited. The real breakthrough came when we started thinking about electrons. And this is the part you absolutely need to remember. Oxidation is loss of electrons. Reduction is gain of electrons. The easiest way to remember this for your exams, just think oil rig. Oxidation is loss, reduction is gain. Seriously, write that down. OIL rig. It's a lifesaver.
And here's the beautiful part. They're a package deal. You just can't have one without the other. It's like a dance. If one atom is giving away electrons, another one has to be there to accept them. They're perfectly paired, which is exactly why we smash their names together. Reduction and oxidation gives you redox. See? It all connects.
Okay, let's look at a classic example, making table salt. You've got sodium, which is an atom that's just desperate to get rid of one electron. And then you have chlorine, which would love nothing more than to gain an electron. They're a perfect match. So what happens? The sodium atom gives away its electron. It gets oxidized. Remember oil rig? It's a loss. And the chlorine atom grabs that electron. It gets reduced. A gain. It's this simple transfer, this give and take of an electron that creates the stable stuff you sprinkle on your food.
Now, that last example was pretty straightforward, right? Sodium gives, chlorine takes. Easy. But what happens when atoms are just sharing electrons, not completely giving them away? It gets a little messy. So how on earth do we keep track of who's winning the electron tug-of-war? Well, chemists came up with a brilliant tool for this, and it's something you're going to use all the time, the oxidation number.
Okay, what is an oxidation number? The best way to think of it is as a kind of accounting system for electrons. It's not a real charge, it's more of a, let's call it a bookkeeping number. What we do is we pretend, just for a second, that every bond is 100% ionic. We pretend that the atom that likes electrons more, the more electronegative one, gets to take all the electrons in the bond. It sounds a little weird, but trust me, this little trick gives us an amazingly powerful way to see where the electrons are shifting in any reaction. All right, like any good system, this one has rules. And I'm going to be honest with you, you just have to memorize these. No way around it for exams. Rule 1, any element just hanging out by itself, its oxidation number is 0. Easy. Rule 2, a simple ion, the number is just its charge. The next few rules give you the go-to numbers for common players like oxygen and hydrogen, but watch out for the exceptions. And the most important rule of all, the one that saves you every time, is Rule 6. The numbers for all the atoms in a compound have to add up to the total charge. If it's a neutral molecule, they add up to 0. This is your final check to make sure you did it right.
Okay, let's see these rules in action. Look at this reaction. On the left side, before the reaction, we can figure out that copper is in a +1 state and sulfur is -2. Now let's look at the after picture, on the right. The copper is now all by itself, so its oxidation number is 0. And the sulfur has skyrocketed up to +4. So what's the story here? Well, copper's number went down from +1 to 0. It was reduced. And sulfur's number went way up from -2 to +4. It was oxidized. See? The numbers tell us the whole story of where the electrons went.
So now that we have this awesome tool for tracking electrons, we can start to see that redox reactions fall into a few common patterns. Let's go through the 4 main types you need to be able to spot.
All right, here they are. First, you have combination. That's just what it sounds like. 2 things combining into one. Then there's decomposition, which is the exact opposite. One thing breaking apart into smaller pieces. Third is displacement, which is kind of like a chemical tagout, where one element swaps places with another in a compound. And finally, you have the really interesting one, the special case, disproportionation. Let's look a little closer at that one.
So disproportionation is kind of weird, but also really cool. It's a special situation where the same element gets both oxidized and reduced in the same reaction. How is that possible? Well, it starts out in some middle-of-the-road oxidation state. Then, during the reaction, some of its atoms get reduced, going to a lower state, while other atoms of that same element get oxidized, going to a higher state. The perfect example is hydrogen peroxide. The oxygen in it starts at -1, but then some of it gets reduced to -2 in water, and the rest gets oxidized to 0 in oxygen gas. It's like the element is playing both sides at once.
Okay, deep breath. We've arrived at the big one. This is the skill that separates the pros from the rookies, and it is an absolute game winner on exams. Balancing redox equations. There are 2 main ways to do it, and we're going to walk through both. First up is the oxidation number method. This is a super logical, step-by-step recipe. You start by assigning all the oxidation numbers to see who's changing. Now, the absolute heart of this method is making sure the electrons are balanced. The total increase in oxidation number has to perfectly match the total decrease. You make this happen by tweaking the coefficients. Once you've got the electrons sorted, the rest is just tidying up, balancing out the other atoms and charges, usually by adding some water molecules or hydrogen ions.
Method number 2 is the half reaction method, and a lot of people actually prefer this one. The strategy here is basically divide and conquer. You literally break the reaction in 2. You write one equation just for the oxidation part and another one just for the reduction part. You balance each of these half reactions all by themselves, adding water, H+ ions, and, crucially, electrons to make sure everything lines up. Then, you make sure the electrons lost in one half equal the electrons gained in the other, add the 2 halves back together, and boom, a perfectly balanced equation.
All right, we have covered a ton of ground. We know what redox is, how to track it, how to classify it, and how to balance it. So for our grand finale, let's see how all of this connects to something you use every single day: electricity.
So think about it. In all the reactions we've seen, the electrons just jump straight from one atom to another. But what if we could get in the middle of that? What if we could capture those electrons as they're moving and make them do some work for us? Well, if you do that, you've basically just invented a battery. That's all a battery or a galvanic cell really is. You take the oxidation part and you physically separate it from the reduction part. This forces the electrons to travel through a wire to get from one side to the other. And that flow of electrons through a wire, that, my friends, is an electric current. And this is what it looks like in practice, in a classic setup called the Daniels cell. On one side, at the anode, you've got zinc metal getting oxidized, releasing its electrons. Those electrons then travel through the wire over to the other side, the cathode. There, copper ions are waiting to grab those electrons and get reduced. And that little tube connecting them, that's called a salt bridge, and it's super important. It lets other ions move between the 2 sides to keep the charges balanced, so the whole process doesn't just grind to a halt.
So a cool question is, how do we measure the push or pull on electrons for different substances? How do we know how much voltage we can get? Well, to do that, scientists needed a starting point, a universal 0. So they just all agreed that one particular reaction, the standard hydrogen electrode, would be defined as having exactly 0 volts. Everything else is then measured against that standard. It gives us a way to rank all the different half reactions, kind of like a leaderboard, so we can predict how powerful a battery will be.
And there you have it. We've gone from a simple idea, oil rig, all the way to understanding the fundamental science behind batteries. Redox reactions are truly one of the cornerstones of chemistry. So the next time you look around, I want you to think about it. Now that you know the signs, how many things in your everyday life are actually redox reactions in disguise? You'll be surprised.